Okay, any questions?
Bu son soruda hocam hani paradoksla karşılaştık ya. Onu bir açıklayabilir misiniz?
You will see the solution in the solutions of the midterm. You see, it was also one of the solutions in the midterm. We had discussed this thing. We had two materials separated by a conducting plane. The plane was moving with some velocity v in this direction. On one hand, we obtained the B fields in the upper plane and the lower plane to be different. On the other hand, we also obtained the effective currents, and we saw that this was effectively just a conducting plane carrying some total surface current. But if this is the case, then we should obtain the same B field above the plane and below the plane. The mistake we did is that assuming that this is equivalent to this one, they are not equivalent. If you want to describe this system as an equivalent system where you have some free currents and also bound currents, you should say that it is equivalent to this system with a surface current on this plane. There is additional bound current on this plane due to the above material, but that current goes around the loop. Similarly, the lower material, there is an effective bound current, but the bound current goes around the loop. Well, in general, these surfaces are at infinity. They shouldn't contribute, in general, if they were finite surfaces. But they are at infinity. They are infinite surfaces. And actually, this thing, I mean, when we studied solenoids, we had found that the B field created inside a solenoid was actually independent of the size. So the size can be infinite. Nevertheless, you will get a uniform magnetic field inside. One thing we didn't discuss in the class, which was given as a hint in one of the questions, that the B field inside the solenoid is actually independent of the shape of the solenoid. There is no shape dependence. So this thing, you can just think of it as a solenoid carrying one current, surface current. Let's say KB2. This is another one carrying another surface current, KB1. And if you calculate the magnetic field at this point created by this solenoid plus the magnetic field created by this wire, you would actually get the previous result. So there's no inconsistency. The problem with our previous approach was that we were ignoring these surfaces at infinity, thinking that they were at infinity, they shouldn't contribute. But those surfaces are also infinite in size, so they do nevertheless contribute. Other questions? Okay, so this week we will be kind of trying to get to the dynamics, the dynamic equations governing our system. So first let's start with some definitions that we will be using. First, the Ohm's law. Well, you are already familiar with one form of Ohm's law. V is equal to I times R. This was the definition that you are kind of used to. Now we will be using another definition of Ohm's law in this course, that we are basically dealing with current densities. So the current density inside the material, inside the conductor, will be proportional to the electric field at that point. You see, the current density is a local property, and it will be proportional to the electric field at that point, and the proportionality constant is what we call the conductivity. Now the inverse conductivity, which we will also use the symbol rho for that, this is called the resistivity. Well, essentially, this is the local form of the Ohm's law, whereas this expression over here is not the local form. Potential difference between 2 points, so it refers to different points at different positions. So that's why that is non-local. This is the local expression. They are basically equivalent to each other. Now let's do an example. Let's just basically see that they are actually equivalent. Let's look at let's assume we have a conductor of some arbitrary shape. I will assume that the electric field inside is uniform. This is the electric field inside. So J, which is given by sigma times E, is also uniform. So this is the electric field is along this conductor. Now the current is defined as the J dot ds. Well, this is my surface S. It is perpendicular. I can take it perpendicular to the current. So the J is uniform. So this is nothing but sigma times E, E being the magnitude times S. This is the current running through my system. Well, the potential difference, let's say this is my H. V is nothing but E dot dl. Well, if you like, minus E dot dl. I will just ignore the signs because in the conventional Ohm's law over here, V is equal to I times R. Everything is defined as positive or the absolute values. So E is uniform. I can just take it out. So this is nothing but E times H. Or the electric field in my conductor, the magnitude, this is equal to V over H, and hence the current is sigma times S over H times E, V. Which is defined as V over R. R being 1 over sigma times H over S, or rho times H over S. This is the resistivity expression that you should probably remember from your first year. Well, this local expression will also be easier to use if we have some arbitrarily shaped conductors. For example, let's look at a cylindrical resistor. So we have another example. We have a cylinder. Inside we have another cylinder. So this is our shape. So what is the resistance for currents running from inside to outside? So let's say we attach this to a battery. We attach the inner surface to one battery, one terminal, the outer surface to the other terminal. So what will be the current running through it? And we should determine the current running through it to be able to determine the potential. Now, for simplicity, let's just assume that inside the battery keeps some charge density, surface charge density inside and also outside. The whole system should be neutral. So let's say this is, let me draw it a bit larger. This has radius A. On the outside, we have radius B. Let's say in the inner side, we have a surface charge density sigma. On the outer side, we have a surface charge density minus sigma. This will be what will be creating the potential difference. Minus sigma prime, sorry. Our system should be neutral because the battery, whatever charge it gives from one terminal, it takes away from the other terminal. But that basically means that sigma times A should be equal to sigma prime times B. This is the relation between sigma and sigma prime. And so we first need to determine the electric field. Now, to determine the electric field inside, we can just, let's say, take such a Gaussian surface. Or on this other image, this is our surface that I'm imagining, of radius, let's say, S, and height H. So for this Gaussian surface, E dot ds over that surface should be equal to Q enclosed charge divided by epsilon 0, but enclosed charge is nothing but 2 pi A times H. This is the total area enclosed of the inner cylinder times sigma. This is the charge density divided by epsilon 0. On the other hand, for the same surface, E dot ds, well, there won't be any contribution from the top and the bottom of the cylinder. There will be only contribution from the sides, and the contribution will be 2 pi S times H. This is the total area times the magnitude of the electric field at the distance S, because we already know that the electric field should be radially out, away from the axis of the cylinder. So we can determine E of S. This is equal to 1 over 2 pi SH multiplied with 2 pi A H sigma over epsilon 0. H cancel, 2 pi's cancel, and we end up with A sigma over epsilon 0 times 1 over S. This is the magnitude of the electric field. Now we can determine sigma by relating this to the potential difference that we apply. So the potential difference that we apply, which is minus E dot dl, this is equal to the integral, if I just assume a radial line going from the inner to the outer cylinder. So this will be just E dot ds from A to B, or this will be equal to A sigma over epsilon 0, 1 over S ds from A to B, A sigma over epsilon 0, logarithm of B over A. This is the potential difference. So by knowing A, B, and V, I can determine what sigma should be. But I will not need it actually. Now let's look at the current running through my system. Now the current is J dot ds. Let's just take, well, we can use the same surface, the side of that red surface, to calculate J dot ds. That we can evaluate the total current running through a length L. So this would be ES ds. Of course, the current is running only through the side of my cylinder. So I'm just evaluating, well, you see, since the current should be conserved, I'm basically integrating it over this surface. I'm calculating the current running through this surface over here. Of radius S also. So this integral is over the blue surface. And this would be equal to, well, J is the current density sigma times E. And so this would be equal to sigma times, well, the electric field is A sigma over epsilon 0 times 1 over S times the surface S. Well, this S is the distance from the central axis. Over the cylinder, it is just constant. I can just take those out. Sigma, okay, so So let me call these sigmas over here sigma tildes. Because I have the surface charge density, which I call sigma. I have the conductivity, which I also call sigma. Sigma tilde is the surface charge density. So these are my sigma tildes over here. But this is my conductivity. J is conductivity times the electric field. So this is sigma times A sigma tilde over epsilon 0, 1 over S. You see, S is constant in this integral. And the total area is 2 pi S times L. This is the current running through the cylinder of radius S and length L, this blue cylinder. And you see S cancels, as it should. Because you see, the current running through this blue cylinder should be the same whether it is small or large. Otherwise, it will tell me that there is a charge accumulation somewhere, where in this problem, still we don't consider charge accumulation anywhere. Charge shouldn't be accumulated. We are still considering steady systems. So it should be independent of where I put this cylinder, this blue cylinder, and hence that is actually what I obtain. So the I is just conductivity A times sigma tilde, which is the charge density, times 2 pi L over epsilon 0. Well, I also know that V is equal to A times sigma tilde over epsilon 0 logarithm of B over A. Resistance is just V over I. So I know the potential difference. I know the current running through my system. Now I can determine the resistance of my system. Resistance per length L. So this is equal to conductivity A times sigma tilde 2 pi L over epsilon 0 divided by V is A sigma tilde divided by epsilon 0 logarithm of B over A. I is sigma times A sigma tilde over epsilon 0 times 2 pi L. Well, A sigma tilde epsilon 0, they just cancel. So the resistivity of this cylindrical conductor, resistance is 1 over sigma logarithm of B over A divided by 2 pi times L. Well, the inverse dependence of L kind of makes sense because if we have it larger, it is essentially there is a larger area for the current to pass through. So the conductivity should drop just like the conductivity of this rectangular resistor. Not rectangular, but prismatic resistor. So this S, this dependence on S of this resistor is basically the same thing as this dependence of L. Furthermore, as B over A gets larger, my conductor becomes thicker, the current should pass through more material, so the resistance should increase. Well, it doesn't increase linearly in this case, so that was kind of not so easy to guess to start with, but at least this relation tells me that as B over A gets larger, the resistance does increase. And it is proportional, inversely proportional to the conductivity or proportional to the resistivity.
Hocam bu kapasitör mü şimdi?
No, it's not a capacitor. It's a conductor.
Ama arasında boşluk var.
No, it's the it's filled with a conductor. So there's a current running through it. Well, these charge densities, sigma tilde and sigma tilde prime, they don't stay there. So constantly, charges are moving from inside to the outside, but the battery is picking them up and putting them back inside, or the other way around, depending on which terminal you are connecting it to which side. So whatever the shape of your conductor is, what you need to do is, well, first calculate the potential difference, calculate the electric field, and the corresponding potential difference. Well, once you know the electric field, you basically know what the current density is in your conductor. And once you know the current density, you know the current, you know the potential, take the ratio, that's your resistance, no matter what the shape is.
Peki hocam şu hani bir oran yazdık ya bu yukarıda.
Mm-hmm.
Onu neden yazdık?
Well, what the battery does, you say, it puts some charges inside, takes away some charges from outside. The same amount of charge that puts here, it takes away from the outer surface. Well, the outer surface is larger, so the surface charge density of the outer surface is less than the surface charge density of the inner surface, so that the total charge in the inner surface and the total charge on the outer surface are the same. But this tells me that the surface charge density on the inner cylinder is related to the surface charge density of the outer cylinder through that relation. B is larger than A, so sigma tilde prime, which is the surface charge density outside, is smaller than the surface charge density inside. Of course, if these were spheres rather than surface cylinders, then I will get sigma times A squared is equal to sigma prime times B squared. So the idea is sigma times the area of this inner cylinder should be equal to sigma tilde prime times the area of the outer cylinder. Now the area of the cylinders are just 2 pi times the radius of the cylinder times h. 2 pi is the same for both the inner and the outer cylinder. H is the same for both the inner and the outer cylinder. So 2 pi a times h of sigma is equal to 2 pi b times h of sigma prime. 2 pi h I can cancel. This is what remains.
Bu sigmalar pile bağladığımızdan dolayı mı geldi yoksa orada zaten var mı?
Well, there's a current running through it. What is driving the current? It's the battery. So once you connect the battery, it will build these currents and these charges will leak through the conductor to the outer side.
Peki hocam bu hani bataryayı böyle bağladık ya. Akım şöyle bir yol mu seyrediyor yoksa komple hepsinin içinde dolaşıp böyle mi geçiyor?
Well, we are basically assuming, we are ignoring that the wires are point-like, they just connect at a point. Ideally, all the terminals should be connected to all the inner surface and all the outer surface, not through a point. Of course, that's an approximation. Or you can say that the terminals are made, the inner and the outer cylinders are made from a perfect conductor. So no matter where you put the charge, it's just distributed homogeneously over the inner and the outer cylinder. These, you can think of them as perfect conductors In between, there is an imperfect conductor with a conductivity sigma.
Peki elektrik alanı nasıl sabit oluyor? Sonuçta bir akım var.
Well, it's not constant. It changes from point to point. But a good question, how come we have an electric field? We are talking about conductors. It's not electrostatics anymore. There is the battery. So you see, when we were discussing conductors, what we had said was, okay, if the electric field is constant in time, in that case, what would happen is the charges in the conductor will move in such a way that they will cancel the applied external electric field. So basically, if this is a conductor, you put some charges in the inner cylinder, some opposite charges on the outer cylinder so that the system is neutral, the inner charges will move through the conductor and they will just neutralize. So no charges, no electric field. But then we have the effect of the battery. The battery takes these charges from the outer cylinder, puts them back in. So the system is never in electrostatic equilibrium.
Yani pil bitince elektrostatiğe dönüşüyor.
Sure, if you remove the battery also, the system is back in electrostatics because nothing is now moving the charges from outside to the inside. In that sense, it's not a capacitor also. In the capacitor, there is no current flowing through one plate to the other plate. But here we have a current running from the inner cylinder to the outer cylinder through this conductor. So it's not electrostatics, so we can't have electric fields inside. Now the other question, you see the electric field is kind of the force acting on a unit charge. Okay? Force is proportional to acceleration. Current is proportional to velocity. How come J can be proportional to the electric field? You see, the force acting on unit charge should be equal to mass of that charge times its acceleration. J, on the other hand, let me just put this sign, is typically charge times the velocity. So how come they are proportional to each other? The charges should be constantly accelerating. And hence the current should be constantly increasing if there is a uniform electric field, let's say. But we just see that if there is a uniform electric field, the current density is also uniform. It doesn't accelerate with time. If the electric field is time independent, current is time independent.
There must be some other force.
Such as?
I don't know, due to material.
What kind of a force due to material? Well, the gravity is, ignore it. It's so small.
Resistivity desek.
So is that a force? So what does the resistivity do? Well, you're right. There is another force acting on the charges, not gravity. So what is that force?
Manyetik force olamaz.
Collisions.
Forces due to the collisions. Well, you see, they are not moving in vacuum. If they were moving in vacuum, then we don't have Ohm's law. Ohm's law is not valid all the time. It is valid for quite a number of, quite a wide variety of circumstances like conductors, but it's not valid all the time. And for plasmas, for example, Ohm's law would not hold because there are not many collisions there. So just, for example, the example in your book is just think of yourself driving in the city where there are lots of traffic lights. Well, the traffic lights just stop you. Right? So you keep accelerating between traffic lights, but the lights constantly stop you, and you start from zero. Almost all your time, you keep accelerating, but nevertheless, your velocity doesn't exceed some average, some typical value. And you are traveling with an average constant velocity. Your average constant velocity will be basically your acceleration times the time you see, what you are doing is if you draw your speed as a function of time, this will be your velocity as a function of time. And when you hit a traffic light, your velocity speed goes to zero, you start again, etc. So you have an average speed. This is 1/2 times 0 plus the maximum speed, more or less. And this is 1/2 times your acceleration times kind of, let's say, the average time between your two stops, or in the case of the electron, the average time between two collisions. And you see that the average velocity, the current density, is basically proportional to the average velocity, but the average velocity is typically proportional to the acceleration. And hence, the current density is proportional to the acceleration, which is proportional to the electric field. What is the average, though? Let's say lambda, average distance between collisions. So what is lambda? What is the average, sorry, in terms of lambda? Lambda over V average, if you want. Well, if we say so, then we have a problem, though. V average is proportional to square root of the acceleration. So again, the velocity is not proportional to the acceleration, which Ohm's law kind of seems to tell us. But you see, the problem is this is not true. In the sense that if you consider the electrons in a metal, they are moving quite fast. Almost. Well, their speeds are of the order of 1% of the speed of light, maybe a bit less. But you see, their direction of motion is completely random. So let's say it starts here, it is moving with some velocity in this direction. It collides, bounces back, collides, keeps colliding. But it's just, since it's after the collision, its direction of velocity is kind of random. It just, on the average, stays where it is. So just think of like a small kid. If you have observed small kids when you're in a shopping mall, they just randomly run here and there, but their average position is always their parents. If the parents are moving, then they will, again, just almost randomly run here and there, but they will slowly drift with the parent. So that's what the electric field does. So this is when E is equal to 0, and when E is non-zero, let's say in this direction, the electron, again, it just randomly collides. After the collision, the direction is kind of random, but nevertheless, you see, it started from here on the average. Now on the average, it's somewhere over here. The electron is drifting. After it each collision, it just loses the velocity due to the applied electric field. But nevertheless, it still has its velocity. So the average time between collisions is actually lambda over, let's say, V thermal. This is due to the thermal motion of the electrons, which is quite fast. So again, we recover. So we said that V average is typically 1 over 2 times A times T average between the collisions. This is also V drift, the drift speed. So this is equal to 1 over 2 A times lambda over V thermal. Or let's put in some more factors we know, 1 over 2 lambda over V thermal. Well, we know what A is. A is the force per mass. So the force is the charge times the electric field divided by the mass of the charge. So this is our drift velocity. J, which is the charge density, let me put rho cube, meaning it's the charge density times the velocity of these charges, which is on the average is the drift velocity. Well, the charge density is the number density of the charges times Q, and the drift velocity is 1 over 2 lambda, another Q divided by V thermal times MQ times E. So typically, this is what your sigma is. Okay, at least in this classical picture, yes. Well, this expression, don't take it to be too precise, but it does capture some of the basic properties that we also observe. For example, if you increase the temperature, well, the thermal speed should increase, so the conductivity should decrease. Well, that is something that we actually observe. At larger temperatures, the conductivity is smaller. And, well, what else we can check? Well, that's basically what we can check only. For a given material, NQ is fixed, lambda is fixed, mass of MQ is fixed.
Hocam bu termal velocity'yi nasıl hesaplayabiliriz?
Next year you will calculate it in statistical thermodynamics.
Rho dediğimiz charge density değil mi?
Rho Q is the volume charge density. Nothing. I mean, you see they are equal. V average in such a motion is called V drift.
What is that 1 over 2 coefficient?
Average. If something is accelerating with constant acceleration, the average velocity is the initial velocity plus the final velocity divided by 2. Again, as I said, don't take this calculation of sigma too literally. It will probably give you a correct answer with the same order of magnitude, but not the exact correct value. Especially we know that at very low temperatures it fails. For example, it doesn't predict superconductivity. At very high temperatures, it should also somewhat fail because the material will start melting, which is not in that derivation. Well, let's do one more example and then you can go for a break. Let's take this spherical conductor. Well, just if you take the cross section, this is what you get. There's a larger sphere, and inside there is a cavity. Just imagine the outer shell and the inner surface as the terminals of your battery. And you attach some battery. So what is the resistance of this system? It's a sphere. These are the same thing. Well, the trick will be basically the same. Again, the battery will create some surface charge densities both on the inner surface and also on the outer surface. On the inner surface, let's call it sigma tilde. On the outer surface, it will be minus sigma tilde prime. And let's say the inner sphere has a radius A, the outer sphere has a radius B. So sigma tilde A squared should be equal to sigma tilde prime times B squared. Well, we don't actually use this relation anywhere, but if you just need it, this is how they should be related. Well, the electric field created by the charge on the inner cylinder inside the conductor will be just as if that's of a point charge. So we already know what the electric field, the magnitude of the electric field should be. This should be equal to 1 over 4 pi epsilon 0 times sigma tilde times 4 pi A squared divided by R squared. This is the total charge on the inner surface. This is the 1 over 4 pi epsilon 0 Q over R squared electric field. The potential difference is just E dot dl. If we just take a radial line segment connecting the inner surface to the outer surface, this is equal to 1 over 4 pi epsilon 0 sigma tilde 4 pi A squared divided by R squared times dr, R going from A to B. And this will be equal to 1 over 4 pi epsilon 0 sigma tilde 4 pi A squared times 1 over A minus 1 over B. This is the potential difference in terms of that sigma tilde. Now let's calculate the current. Let's say the current passing through this surface. Well, since there are no accumulation of charges, whatever surface you choose, the current passing through that surface should be the same. So let's say this surface has radius, let's just say R, capital R. So the current running through that surface is E dot ds. Well, the electric field is radial. The S vector is also in the radial direction. Sorry, it's J dot ds, which is sigma times E dot ds. Again, electric field is in the radial direction. ds is in the radial direction because we just take a spherical surface. So this is equal to sigma times 1 over 4 pi epsilon 0, sigma tilde 4 pi a squared over capital R squared times ds. On the sphere, R is just a constant. So I can take everything out. So I will be 1 over 4 pi epsilon 0 times sigma tilde 4 pi a squared divided by R squared. Well, the integral of ds gives me the total area of this blue sphere, which is 4 pi R squared. And as you see, R squares cancel. And hence, again, the current is independent of the radius of the sphere over which I'm evaluating this current, as it should be. So these cancel. Let me also cancel these ones. So we obtain sigma tilde times 4 pi a squared. And this is equal to I times epsilon 0 over sigma. I know the expression of V, we had already evaluated it. So V is equal to 1 over 4 pi epsilon 0, sigma tilde 4 pi a squared times 1 over a minus 1 over b. This is the expression we evaluated on that first line. Well, this 4 pi a squared sigma tilde, we had evaluated that one also. This is equal to 1 over 4 pi epsilon 0, I times epsilon 0 over sigma times 1 over a minus 1 over b. If we identify this with I times R, the resistance of this system is just 1 over sigma. Well, as usual, it's proportional to the resistivity or the inverse conductivity multiplied by 1 over 4 pi times 1 over a minus 1 over b. So this is the resistance of my system. Again, independent of whatever the shape of your conductor is, if you can identify the electric field, then you can identify the potential difference and you can calculate the total current running through the system. Just take the ratio, that gives you your resistance.
What happened to negative sign, to minus sign? V is equal to minus.
Well, you see, that minus sign is over there, but when we say V is equal to I times R, by definition, V is positive, I is positive, R is positive. So this is not really the potential of the first terminal minus the potential of the second terminal. This is the potential difference between the two. Just take the absolute value. So that's why here in these calculations, I just throw away the minus signs.
Hocam şey yaptık mesela ters bağlasak içerideki eksi olsun dışarıdaki olsun.
Well, I don't know whether sigma tilde is positive or negative.
Bana nasıl olur yani fark etmiyor.
I don't know what sigma, it doesn't matter. The resistance doesn't matter. Well, of course, in such circuit elements, which way you connect is not important. The resistance will be the same. These are not directional resistors. For example, you also have diodes, which have almost infinite resistance in one dimension, in one direction, but almost zero resistance in the other direction. We are not studying those things. We are just looking at simple conductors.
Hocam bir şey sorayım. Şimdi bu kürenin yapıldığı maddeden silindirik şey yapsak ikisinin direnci farklı çıkıyor.
Well, from a sphere, you cannot obtain a cylinder.
Yüklü olsaydı başladım.
Well, it's a conductor. So well, how does a conductor behave? You see, if you had an initial charge and then you connect it to a battery, and let's assume that the battery doesn't change the total charge of your system, well, the total charge will just be on the outer surface. It will affect nothing.
Ama içerideki şeye etkilemeyecek mi dışarıdaki yük?
Well, in a conductor, all the charges just move out. Of course, the battery is just putting them back in, but it only puts back in what it took from out. So there is this additional charge you put. The battery will not affect it. It will just move out. Let us also make one more proof, and then you can go for a break. You see, we looked at this conductor. And then we said that let's assume that it is the electric field is uniform inside. Let's prove that the electric field is uniform inside. Well, of course, we also need to pay attention to how do we connect this to a battery. So that will be crucial here. So I will make this assumption, that the terminals are connected on the surfaces. So this is my terminal. This is the other terminal, which are connected to my batteries. And these are made up of perfect conductors. So since they are perfect conductors, there won't be any electric field inside. You see, J is equal to sigma times E. J is finite. If sigma is infinite, E should be 0. That means these terminals are equipotential surfaces. My conductor is not an equipotential surface anymore because there's an electric field there. But my terminals are equipotential surfaces because I'm assuming they are perfect conductors. So what we know, the potential on this side is constant, which we can just choose to be 0. The potential on the other side is also constant, which we can choose to be V0. There is no current running out of the size of the surface of my conductor. So J dot N is equal to 0.
Nasıl yazılıyor?
Here, you see J is the current passing through a surface per unit amount of time, is the charge passing through a surface per unit amount of time. Now, I have this surface. I look at the normal component of the current. Well, the current is not getting out of my conductor. It's always inside my conductor. So there's no current running out. The normal component of the current should be 0. Well, this means that En, the normal component of the electric field, is 0 because J is proportional to the electric field. Well, this basically means that the derivative of my potential, its normal derivative, should be equal to 0 on the sides. Now, these are my boundary conditions on the potential. Well, let's say V.
Hocam bu V ile şu potansiyel fark aynı değil mi? V0.
Sure. No, you see, V is just some function. I can always define this potential everywhere. But I know I'm trying to figure out its boundary conditions. It has to have the zero value on the surface everywhere. It has to have the value V0 everywhere on the surface. And its normal derivative should be 0 on the surface of my conductor. So these are my boundary conditions that V should satisfy. So let's see, this is my, let's just define this to be my z-axis. Let's assume my conductor has a total height h. V is equal to V0 over h times z. I'm just making it up. Does it satisfy the Laplace equation? There is no accumulation of charge anywhere, so the volume charge density is 0 everywhere. So my potential should satisfy the Laplace equation. So it satisfies the Laplace equation. It should also satisfy these boundary conditions. Now, I'm making this, I'm just guessing. Does it satisfy the Laplace equation?
Hocam şimdi körün akım var diyoruz. Akım şeyin içinden geçiyorsa charge var.
Well, let's see. J is equal to 1 over sigma times E. Divergence of J, this should be 0 because there's no accumulation of charge anywhere. We are still, in a sense, in a static case in the sense that there's no accumulation of charge anywhere. But this is equal to 1 over sigma times divergence of E. So divergence of E is 0. So my potential should satisfy the Laplace equation. Now again, this is just a guess. It does satisfy the Laplace equation. Laplace equation in Cartesian coordinates is just to take the second derivative with respect to x, which is 0. Take the second derivative with respect to y, it is 0. Take the second derivative with respect to z. Well, the first derivative is non-zero, but it's constant. The second derivative is 0. So this does satisfy the Laplace equation. Well, let's see. Does it have the 0 boundary value at this boundary? This function, z is equal to 0. So it does have this value. On this boundary, does it have the value v0? Well, z is equal to h, so v is equal to v0. Does it satisfy this condition? Well, the normal derivative is the derivatives with respect to either x or y or some combination, because the normal component is perpendicular to z direction. Well, it doesn't depend on x, it doesn't depend on y, so its x and y derivatives are all 0. So it satisfies the boundary conditions, it satisfies the Laplace equation, and then I have my uniqueness theorem. And the uniqueness theorem tells me that since this solution already satisfies my differential equation with the boundary condition, it is the solution. There's no other solution, but this tells me that at least inside my conductor, the electric field is nothing but V0 over H in the Z direction. And hence the electric field is uniform in such a conductor. You see, this is inside the conductor. We don't know anything about what is the electric field outside the conductor.
Here you said J is equal to sigma E. Here you said J is equal to 1 over sigma. Where is this formula coming from? V is equal to V0 over H times?
I made it up and then show that it is correct.
Yani hocam şimdi bateri olduğu için akım sabit dedik, ondan mı bu delta J sıfır?
What I said is there is no accumulation of charge. So why is there not any accumulation of charge? Let's see. let's take such a band. There is a battery, there is a switch. Maybe it will happen that when I close this switch, there will be some accumulation of charge at this band. I mean, the charges might not be able to go around, let's say. So there will be some positive charges here, accumulated, who knows. But then there will be an additional electric field due to these positive charges. And this additional electric field due to these positive charges will try to prevent any more positive charges from coming, and they will be pushing the positive charges in this direction. So they will slow the current over here and increase the current over here. And there will be an accumulation until the current that comes in is the same as the current that goes out. So basically, the system, maybe at the moment that I close the switch, there might be some accumulation of charges somewhere, but the accumulation of charges will be such that in a very small amount of time, these accumulated charges will distribute themselves so that the current will, and no more accumulation will occur. It might happen for a small amount of time. And then after that time passes, we are back to our steady current configuration, where there won't be any more accumulation of charges.
Yani girenle çıkan birbirine eşit oluyor.
Yes.
Normalde de devrelerde zaten giren akımla çıkan akım eşit değil mi?
Yes. That's what I'm saying. That's what we are proving, kind of. At some times, I mean, for example, at the moment that I close the surface, that will not be the case. But when the steady currents are reached, that will be satisfied. Now, steady currents are usually currents that do not change in time. But even, I mean, this accumulation of charges and then setting the same current everywhere happens so fast that even with our city electricity, which is at 60 hertz, well, even if you go to much higher frequencies, I mean, it's a good approximation.
O zaman bu sistem ideal bir sistem.
In which sense? Well, there are some idealizations over there, assuming that the terminals are ideal conductors, perfect conductors. But usually the terminals are made from almost ideal conductors. So that's not such a bad approximation. Well, most wires will have a uniform cross-section. So that's also not a bad approximation. Not a bad idealization. The bends and the charge accumulation, well, most of the time it takes for that accumulation to build up is negligible. So when you look at your circuit, there won't be any accumulation of charges anymore. Yes, it is an idealization, but works almost perfectly for most practical purposes. Okay, let's give a 10-minute break, and then we will continue.